Hi guys. In this video I'm going to talk a little bit about another type of simple harmonic motion, but this time I'm going to talk about a pendulum. Basically it's a string with a mass attached at the end, and it's allowed to swing in an arc, right? And we're going to try to derive the formula. But before I do that, let's talk about the energy. So when I raise the pendulum to here, when I raise this bob, the mass here to this level here, at that point I have all gravitational potential energy with respect to this point down here. And then when this thing swings, I lose all my potential energy when I'm here to kinetic energy. So you have your maximum kinetic energy here. Now, so that's in terms of energy, which is something that we've already done. Now let's talk about the acceleration. Where is the acceleration maximum? Where is the acceleration minimum? And that has to do with the restoring force that I'm going to show you. We're going to discuss proof about. Now, when you are up here, you have the furthest displacement from equilibrium. The equilibrium is this dot here. So we're looking at what's happening along this line here. And I'll get to that in a sec. So, and I think we learned for springs that when the displacement is the greatest, that's when you have the maximum force and the maximum acceleration. So your acceleration right here, I'm talking about the tangential acceleration, not the centripetal. Your acceleration here is 0. Okay, but you're still going to deal with centripetal acceleration. Now, what I want to do now is that I want to talk about this restoring force, and I'm going to show you proof to where the formula comes from. I'm going to use some analogy with springs. So if I'm looking at this mass here, at any point, this doesn't have to be the end. So I have some tension here, okay? So I'm going to say this is tension. Okay, and I have mg down here. Okay, now I'm going to look at the oscillations along this line here. So this is my x-axis kind of. Okay, this is the positive values for x. This is my 0, and these are my negative values for x. Okay, and so this is kind of like oscillating back and forth. It's also doing this. But you can see clearly, and that's the first approximation that I'm going to do. You can see that the displacement up and down, if the angle is small, and that's the condition, if the angle is small, this height here is nothing compared to this displacement. So I think we can say, well, you know what? The acceleration is just happening horizontally. So which means the restoring force is just whatever is horizontal. So here are my forces. So I'm going to take this t, I'm going to break it into a t in this direction, and you can probably see, hopefully you can see that this angle here is theta. So this is going to be t sine theta. And then I'm going to break it into t cosine theta. Okay. Then let's do the F net equals ma. Now we're looking at to prove the formula for period of a pendulum. So F net equals ma. It just means I have to find the F net. Now, if that's the positive direction for x, let me just make sure I'm recording here. Yeah, we're rolling. Okay. It looks like it has to do with t sine theta. But the net force is pointing to the left, so I think there is a negative here. And that explains why we call it a restoring force. It always wants to bring you back to this equilibrium position. Equals m times a. All right, now you have to open your minds with me here. Okay, if the angle is small, for small angle, this is the small angle approximation. If the angle is small, sine theta is equal to theta, as long as you are in radians. So, and you can try that. You can find, let's say, 8 degrees in radians, and do the sine of that angle and do the angle itself, and you're going to find that they are very, very similar. The other thing I'm going to do, I'm going to assume that there is no acceleration up and down, because as you can see, the change here is very little. The displacement in the y direction is extremely small. So that I can say that t cosine theta is about equal to mg. That's another approximation. And another one. So for small angles, and you can prove that yourself in the calculator, as long as you are in radian mode, cosine of small angles is about 1. Close, 0.999. You can try that. So now I'm going to come in here and I'm going to replace the tension with mg. Okay, and I'm going to leave it like this. I'm not going to cross out the m's yet. Okay, now if you look at here, you guys did this in math. This arc length here, this is what you guys call S, I guess, right? So that S is equal to the length times the angle in degrees. Okay. Well, that S, and that S doesn't have to be all the way here. It could be anywhere, right? Okay. I mean, I could have started from here, so it doesn't have to be from the end. You could have started here, and this will be the S. You can see that if, as long as the angle is small, so I make this angle smaller and smaller and smaller, this S becomes closer to the displacement X. I hope you can see that. Again, this angle is too big, but if you make the angle small enough, you can see that S is almost X. So I can change that with displacement X, which means theta, so I'm gonna write it like this. Theta is X over L. And I'm gonna move the L over to here, and I'm gonna put the X here. This is equal to M times A. Well, this should look familiar. This is very similar to negative Kx equals Ma. So I'm using an analogy with the springs. Now for the springs, what did we do? We said, well, the period is 2 pi square root of M over K. Well, the K is kind of like that. So this is mg over L. And if you play with this a little more, so the mass crosses out, so it's independent of the mass, the period that is, and you get 2 pi square root of L over G. Okay, so this, I had an old proof for this. I was kind of like just trying to come up with an easier way of doing it, but this is the real way of doing it. So you're gonna see that I'm gonna change, but just when you see me changing, that's just the old video. So this portion here is the new one. Okay. T is independent of amplitude. Okay. So if I pull, okay, with a small angle, or if I pull with a larger angle, it doesn't matter. So you're going to get the same period. So I'm going to let you try this while you're at home. So I'm going to pull this, and you can start anytime you want. You can do 2 cycles if you want. Okay. So now, if you do the period there, or if you do the period with a smaller angle, you should find them to be the same. And the reason for that is when I go with a bigger angle, my speed at the bottom, I'm going to be moving with higher speeds because now I have more potential energy, okay? But I'm going to cover a bigger distance, just like with the spring. So those 2 things kind of cancel out, okay? So the amplitude doesn't matter. The amplitude here, I mean the angle. T is directly proportional to the square root of L. So in other words, if L increases, the period should increase. So for longer strings, okay, it's going to take longer to go back and forth. And I can see that T is independent of mass. Okay? And I think we talked about this in the past conceptually, that so I'm going to pull this at about here and let them go. They should be in sync, right? And they are in sync, right? Which means the mass doesn't matter for the most part because I didn't do it exactly the same angle. So hopefully that's the same angle. So if I let them go, okay, they're pretty much in sync in the very beginning. And I think we said in the past that because technically this mass is falling, it's just falling sideways, it's not falling straight down, and we know that all objects fall at the same rate in the absence of air resistance, basically, right? So T is independent of mass for that reason, okay? Now, T is directly proportional to square root of L, meaning if you have a long string, it takes a long time to get there and back. If you have a shorter one, okay, it's quicker, right? So the period here is shorter. Now, so I made this shorter one about half the length of this longer one, right? So I'm going to ask you to calculate the period of the longer one, the period of the shorter one, and compare them. And based on this formula here, the period of the longer one should be about radical 2 the period of the shorter one, because the longer one has a length that's twice as much as the shorter one. So that 2 comes out as a radical 2 on the outside. So I'm going to let this go. You can try maybe 2 or 3 cycles, find the period, okay? All right, that should have been enough for you to collect data. Now you try this one and see if that relationship holds. Okay? And so try this stuff here, and then the rest of the pendulum is really similar to what we did with the springs. Have a nice day.